have a question.
Yes.
How come that the acid is weaker when you consider carbon dioxide as like this in the starred one?
Because carbonic acid is on the second line here, and that is an acid that is a real acid that disintegrates into hydrogen ions and hydrogen carbonate. But carbon dioxide dissolved in water need to react with water first in order to produce carbonic acid. So if most say that the contributions to H2CO3 star is 1 carbonic acid and 100 carbon dioxide aqueous. So most of the molecules in the starred version here, they are non-active as a strong acid. So that is essentially as diluting a quite considerably stronger acid with an inactive with an inactive solution of dissolved carbon dioxide. But it's still quite convenient because the first two of these equilibria occur all the time. And as long as a true carbonic acid has been formed, there is a possibility of its dissociation. And then, of course, it's depleted in the amount of carbonic acid, and then some more carbon dioxide may form new carbonic acids. But together, all of the carbons that these two first reactions represents, they can be clumped together in the third line here. And then if you see in the table below here, the acidity constant of the first, or the equilibrium constant of the first one, and the acidity constant of the real acid, the product of these two is the acidity constant of this star version. This is perhaps it would have been simpler if we did just remove this second equation and forget about the real acidity constant of carbonic acid compared to the effective acidity constant, which is 6.35 the pK values. I don't know if I explained or
yeah, I think I understand. Yeah. Like it's not really that it's weaker, but the denominator is larger.
Yes. Yeah.
Yeah. Okay.
You see here that the denominator is both the real acid and a lot of dissolved carbon dioxide. And see, this is in the order of 1 to 100 or so. So the major part is the carbon dioxide. And this one usually clumps these two together to this hypothetical carbonic acid, but with a star, to remember that most of this carbonic acid isn't really carbonic acid, but rather carbon dioxide. But for every practical reason, we use this effective acid, carbonic acid, and not the real. I'm not sure how one has been finding this real acidity constant. There is a long story probably. But I'm not sure exactly how they did.
Yeah, thank you.
Yeah.
I'm a bit confused by the final pH of the ocean, looking at these equation,
yes,
like
yeah,
equilibrium. So is it
excellent? This is exactly all people become confused. How about the pH and acidity constants, such things? The pH ratios, they are in between the Ka1 star and the Ka2, but is that just a coincidence, or yeah? Or sorry, maybe I should listen to you why you're confused.
Yeah, it's just, I don't know, for me it's I see acids and I see like finals that are like more basic. Like is it carbonate in English? Yeah. So it's like, for me, is it ±1, or is it more acidic or more basic in the end, like the more carbon dioxide we add?
Yeah. I interpret that as it's very difficult to understand what do these equations actually mean. So perhaps, I mean, if you have you want to calculate the acidity, the pH, then if you know, for example, carbonate ions and hydrogen carbonate ions, then you can calculate it. But all of these are acting simultaneously, at least the bottom two lines here. I recommend we go for, I think the answer will come soon.
Yeah.
This is just another one. I recommend that we go for some graphical representation. This is something I call a logarithmic equilibrium diagram for the different species in the carbonic acid system, both the carbonic acid and the hydrogen carbonate and the carbonate. The P in front of it means minus 10 logarithm. It's like the P in the pH. Now, if you have carbon dioxide from the atmosphere and assume that it is 400 ppm, then looking at this equilibrium, if we should look at 400 ppm, how much is dissolved and how much is then converted to carbonic acid? This will show up to be something like 10 to the minus 4.87 moles per cubic decimeter if the carbon dioxide only comes from the atmosphere in pure water. So that is the reason why we have the line at this position. But I mean, in principle, it's not really important why we have it here. If we increase the pH somehow, then the pH, the carbonic acid will disintegrate into hydrogen carbonate. So the level of carbonic acid will decrease, while the hydrogen carbonate will come from small values here, low concentrations, and increase and dominate here. And then when one increase the pH a lot, then it will be transformed to carbonate ions. We see what we have at the, you asked about the, let me jump a few pictures forward. Here. Here's the same curve, but without any concentration indications. That at acid, the red one is the carbonic acid. At low pH, carbon dioxide, or with looking at it combined with water as carbonic acid. That exists as carbonic acid. The red one means H2A, the diprotic acid. While at 6.35, here is the first pKa value for the carbonic acid star. And then the carbonic acid will decrease all the way. And then in oceans, there is usually hydrogen carbonate indicated here by the blue line or the HA minus. That will rise to a maximum. It won't go up all the way to 100%, but it will be quite a lot. This curve indicates the fraction of the different species, carbonic acid, hydrogen carbonate, and the green one is for the carbonate ions. Now if I claim that in the oceans there is mainly hydrogen carbonate, so we need to be somewhere in between here, in this area, and we can look at the pH. It should be something like 8.35. And this is actually the pH of Lake or the Atlantic Ocean, and similar. I only measured in the Atlantic, so I can't just judge for that. But I think it's the same in all other large oceans. It deviates very, very small values from 8.3, 8.35, a few hundreds maybe. But in the Lake Baltic, it has actually been deviating a little bit, a few hundreds more. So the Lake Baltic is actually a little bit acidified compared to Atlantic Ocean, which is perhaps not unexpected. But what does it mean for living creatures in the sea? Hydrogen carbonate, they don't need that. But do they need carbonic acid? No. But carbonate ions, that is of importance. So carbonate ions is existing in the level of, say, 1 or 2% at the normal pH of oceans. And carbonate ions are necessary for building shells, for example, in those organisms, mussels and snails and such things. A lot of creatures that are using calcium ions and carbonate ions to build shell are dependent on not living in an acidified lake or ocean. In an acidified lake, you will never find any shells, fish or something like that. They simply, the shells, if it's acidified to say 7, which is neutral in some way, the amount of carbonate ions has decreased a factor of 10 or maybe more compared to 8.3. And this is enough for making life a hell for shellfish. So they won't be protected from the environment, and there will be other fishes. Fishes, they don't feel, most fishes don't feel bad at pH 7, but maybe at pH 6 and 5, then only a few fishes tend to survive. It can't be too acidus. I don't think there are any fishes at all in lakes with pH 4. There are pH 4 lakes. This brown small pot lake in pine woods, for example, or they could be extremely acidus, but there are only a few insects living in them. You can taste the water; it's excellent taste of it, but because nothing lives in it except some brown humus subjects, but that is only leached from the forest. So how to, if you want to calculate this pH of of the ocean water, this is quite complicated. It's considerably easier actually if you have one of these fraction diagrams or the logarithmic version of a diagram. The only advantage with the logarithmic versions is that you can see that, for example, the carbonic acid, it starts to decompose here and then passing the first pKa, and then starts to decompose even faster after the second pKa. So carbonic acid is no more hardly 10 to the minus 14 at pH close to 14, but 10 to the minus 14 compared to Avogadro's number is still a lot of carbonic acid molecules. This is difficult to draw these conclusions from these, how to say, equilibrium expressions, even though those equilibrium expressions are the ones that lie behind the shape of these curves. But we should go through some possibilities to use diagrams like this instead of dwelling into a lot of equilibrium calculations. We can't avoid them totally, but perhaps we should get them inside. This hydrogen carbonate acts as an acid producing carbonate ions, but it also simultaneously acts as a base producing carbonic acid. And both of these aspects of the hydrogen carbonate need to be taken care of in the same time. Then you can actually calculate this pH value. I have given such a comparison with the in the text case 4007.pdf. There is a special example on hydrogen carbonate ion that you can't only treat it as an acid or a base. You need to take into account both of those properties simultaneously. But we should, maybe we should avoid doing that, but we can actually rely on these diagrams. The center here, maybe now I should introduce a very, very local. Do you see a line here?
Yep.
This is the simplest possible version of the carbonate system. 6.3 or 4, maybe 35 it was. The accuracy of these equilibrium constants, they are not at all very accurate. But depending on which source you look up, you will have, say, variations in the second decimal for sure. And in the first decimal, probably, maybe, you should have approximately the same unit value. But concerning carbon dioxide, it has been so much studies around that, so those two values are actually quite okay. Here you have carbonic acid, and then you have hydrogen carbonate, and here you have carbonate ions. So the problem is, say that you know that you have a solution with some concentration is say X moles per cubic decimeter or so. If you look at the carbonic acid, then you can treat it as an acid because that is only an acid, nothing else. And if you look on the problem like a base, then you can treat the concentration of that base only as a base because it doesn't act as anything else than a base. But when you come to this ampholytic creature here, the hydrogen carbonate, you need to take care of both the basic character and, or the acidic character and the basic character. This is quite complicated, cumbersome, and it's usually never described in chemistry books. It's just stated that it is both and can act as an acid and a base. And in water chemistry and soil chemistry, maybe one does an example, but then you go for this diagrammatic diagram presentation. Oh, that was not my meaning. The pH axis. So, so, and the question is, my extremely simplified version of this pH question, what is the pH of a hydrogen carbonate solution? Well, this hydrogen carbonate dominates between 6.35 and 10.33. Remember that the pKa value means that the dominant form transform. If you come from the acid side here, at 6.31, there is 50% of the acid left, and you have formed 50% of the hydrogen carbonate. So to the right of pKa1 and to the left of pKa2, the hydrogen carbonate dominates. So if you only have hydrogen carbonate in the solution, or say that you collect the substance sodium hydrogen carbonate, this is bicarbonate that previously one ate this, dissolved it in water if you had a acid stomach or something like that, and then you felt better. I don't know, I never tried it actually. I tasted it, but it tastes awful. What would the pH be? Why not in the center? What is the average value here? It's 8.34. And this happens to be the pH of the sea. So it could be a coincidence, of course, but it isn't. This is a simplification of the so-called logarithmic diagram. You see if I can find the logarithmic diagram. Here's the logarithmic diagram in between. If you only look at the H2CO3 and HCO3 minus and CO3 minus, so between these two pKa values, here is the maximum amount of hydrogen carbonate is around 8.34, 8.3, 8. Don't expect these diagrams to be extremely accurate, but they are kind of accurate within a few hundreds of pH values, which is more than enough. if you measure pH, for example, then yeah, of course, if you should give your data to United Nations for the next IPCC report, then you should see to make your utmost possible accurate values. But otherwise, if you just want to see a quick look, then a tenth or so deviation doesn't matter. So actually, these equilibrium expressions here, they are hardly ever used for doing calculations unless you refuse to accept the graphic character. Then it is a possibility to use a lot of algebra and come to conclusions, but it's not easy.
Lars,
Oh,
would you mind speaking a little bit louder, please?
louder. I can maybe. Is this better?
Yes.
Yeah. Varsågod. Let's look. If we, for the moment, goes to another type of carbon dioxide, the carbonate ion associated with calcium carbonate, associated calcium, that is calcium carbonate, limestone. Calcium carbonate is an insoluble compound, meaning that it is not very soluble, but it's not totally insoluble. Usually, this type of equilibria, they are looked upon with two states. The initial state, we designate what do we start with on both left-hand side and right-hand side. We don't have any calcium ions or carbonate ions from the beginning, but we have calcium carbonate. Why is it a number 1 here? Anyone with a clue?
Solids are usually assumed to not play a role in the equilibrium as they are there in very big amounts compared to the ions.
Exactly. This is more, as long as it is present, and we can say big amounts compared to the ions, if some of it dissolves, then as long as there is still some of it left, it doesn't matter actually. You see here that the equilibrium constant is defined as the right-hand side, the product of the right-hand side divided by the left-hand side. Is only calcium carbonate in the left hand. But these curly brackets mean something special. They mean something called activity. And this is compared to a standard state. The equilibrium constant defined by this, in this sense, do not have any unit. They are all only numbers. And they should be like that, even though a lot of chemistry books denote them with units. For example, moles per cubic decimeter times moles per cubic decimeter divided by, if this would be a concentration, then the unit of this K should be moles per cubic decimeter. This is, it's not rubbish, but it's close to. But you don't need to, we use that for asking questions to students, but except I don't do. We use the activity concept, and then the activity of a solid compound is the same as a solid compound in standard state. So thus the unit doesn't change. For solutions, the activity is nearly like the value of the concentration, because the standard state of a concentration is a hypothetical solution with 1 moles per cubic decimeter. So what is, if you have a, say, 2 moles per cubic decimeter of calcium ions, then you should calculate the activity. So 2 moles per cubic decimeter divided by the standard state, that is 1 moles per cubic decimeter. That means it will be the number 2 here. 2 divided by 1 is 2. But we don't need to throw away this concentration parenthesis, but just skip the unit. Use the value of the concentration, and then use a unit for all pure solid phases, and also all pure liquids. Like water, for example, if you would add in water in this equation, there is aqueous here on the right hand side. Where is that aqueous coming from? Well, let's add a lot of aqueous on the left hand side, but that would appear here in the equilibrium constant expression. But would you, if you have some piece of marble and in a beaker with pure water, then a little bit of the marble would dissolve, but most of it would still be pure water. So you could claim that the water occurring here should show up as a unit, because it's, the solution is nearly pure water. If we say that X moles of this calcium carbonate dissolves, so nothing will be affected. It should be 1 minus X or something like that, because the solid calcium carbonate is still solid calcium carbonate, can't be distinguished from that. It should be only a unit. But on the other hand, it will produce some calcium ions and carbonate ions. So this is a simple equation. Then the equilibrium constant is the x square, or x is square root of the equilibrium constant. And assuming calcite, my source of equilibrium constant states that calcite has 3.36 times 10 to the minus 9. There could be varying sources, but I mean, accepting this, then you will have x equals to 5.8 times 10 to the minus 5, which is the equilibrium activity, or more easily stated, the equilibrium concentration of calcium ions and carbonate ions, assuming that none of them reacts further. This is quite crude approximation, but it's not bad. Well, it could be worse. And 5.8 times 10 to the minus 5, if you take the logarithm of that, that is slightly less than minus 4. And then you take the minus logarithm, so you get something like 4.2. So this is one of these logarithmic diagrams when you have dissolved calcium carbonate in pure water, and assuming that nothing else happens. Then you see that what you have determined by the solubility here of calcium carbonate is essentially only the level in this diagram. Now let's see, can I write in this one? Here is the, do you see my handwriting now?
Yes. Yeah.
And here is the carbonate ions. Then what about these two extra lines? This is the hydrogen ion lines, and this is the pink one is the hydroxide ion line. So pH 0, the hydrogen ions are PC of that is 0. pH 2, hydrogen ion PC is 2. Well, of course. This is just the hydrogen line is just sloping with the slope +1 actually. Note that the positive y-axis is downwards. This is not only for making life a hell for you students, but perhaps we should have stated that it's the logarithm of the concentration, and then it would have been negative values here everywhere. But that we didn't do. We used the P nomenclature. What about the relation between H plus and OH minus? Do you know anything about the product of these two?
I think it's always 10 to the power of -14.
Exactly. And if you go to logarithmic version, you can say that pH and POH should be 14. Or you can say that POH is 14 minus pH. So if this H plus line slopes like that, the OH line should have an opposite slope. POH is a negative value times pH and a constant 14. So what did we have in with the carbonate ion? In a solution, we assume that there is nothing else than carbonate ion in the solution. But this is, then we forgot the water. So this is one way to express that we have a solution with water molecules and carbonate ions. Can we remove any hydrogen ions from that? What I'm going to do now is called the protolysis condition, proton condition. We can't remove them from carbonate, but we can from water, and that would produce a hydroxide ion. Because hydrogen ions are very mobile in water solutions. Can we produce anything? Can carbonate attach the hydrogen ions? Yes, it can actually do that. Then it produced hydrogen carbonate. And water can also attach a hydrogen ion, producing an oxonium ion, which is essentially what we mean that when we type H plus, except that at least I am too lazy to write out all these long molecules. The hydrogen ions that has been moving around, all of them that has found new friends to hang around with, they need to have been leaving from somewhere, because the amount of hydrogen species that has been decreased by an hydrogen ions must be equal to the amount of species that has got an extra hydrogen ions. So this should be valid. Equals the amount of OH minus. Here we have a diagram with a lot of lines indicating this, a lot of things. OH, this is same here on that line. So OH, here is a crossing. Is this somehow valid? This is OH equals to HCO3 minus. This is not bad, 2 out of 3. But what about the hydrogen ions? That's the black line here. That is, at that pH, it's something like 5 units below on a logarithmic scale. So then we can delete that one. So that is a way to graphically calculate the pH of a solution with carbonate ions in water when you don't assume any extra. We just see this as a basic ion. Then we just record it. It will become something like 9.5 or something like that. Note that we don't have a lot of carbonate ion in the solution, but rather hydrogen carbonate, according to this diagram. So actually this statement that we only have calcium ions and carbonate ions is probably wrong, but at least it's less wrong than just guessing widely. Why is it wrong? It's because the hydrogen carbonate, the carbonate ions represented by this blue line, we came to that idea that it should be this very position here because hydrogen ions are moving around in the solution, a water solution, easily, and they will occupy new species and they will leave other species. So that is a way to construct where is the pH of a solution of calcium carbonate. And then in addition to that, we also realize that this is also meaning that, well, it's on a something like half a unit on a logarithmic scale. Here is a factor of 3 or something like that, or 2, maybe. It's at least less carbonate ions than we started with. We started essentially with only carbonate ions, but that is not possible with just dissolving calcium carbonate because it's too unsoluble, too little soluble, and the level of carbonate ions is so small that we can't expect them to become untouched by the water molecules. A bit worrying, but if you would increase this level, say that you would be here on a value of 2 or something like that, that would mean just moving the whole graph above. Then you could actually stay with carbonate ion in the solution. So but which is not possible with calcium carbonate. But with other, if you take sodium carbonate, for example, that is freely soluble in water, a lot more than calcium carbonate. And in that case, you can also claim that you will have the majority of the carbonate ions still left as carbonate ions, because the total concentration is much higher. Clock is 10:51. I suggest we should do a lot of these discussions in future, and perhaps we should try to do some calculations in the afternoon. I'm not sure if you want to do these calculations by hand or construct these diagrams. There is some recipes for manual construction of these diagrams on the back of an envelope or something like that with the paper and pencil in the compendium KZ 4007. So download that to your computer, or otherwise I will show you some computerized a computer program called Medusa that we can draw these diagrams with. This is not done by Medusa, but we will have the same version. I don't think we should spend a lot of time actually trying to realize how to draw these diagrams, but we should spend some time with Medusa to draw diagrams and then interpret the diagrams, because that is, we don't have a full semester course, then we could do it really carefully, but we have a 2-week course. Is it 1 o'clock calculation exercises started?
Yes, it is.
Yeah. So then I suggest that we, well, let's see, how do I stop this? Then fortsätt vara inloggad, yes. There is calculation exercises. There is a small booklet called R for räkneövningar in Swedish. Calculation exercises in English. But here are some, we can have a look at them at 1 o'clock, and I will also introduce Medusa. If you like. Of course, I mean, neither lectures nor calculations exercises are compulsory, but only the labs are compulsory, but I recommend them very much if you want to pass the course and such things. Should we see each other at 1 o'clock? I stopped the recording.